So guys, we arrived at this central PAA block diagram, parameter adaptation algorithm for stability analysis. All the different, whether it's serial parallel or parallel algorithms, can be framed in this block diagram. The differences are what kind of edge in the LTI block look like, and then in the adaptation algorithm, the regressor vector will also be different, right? So that's the differences in the scheme. And when the adaptation gain is a constant, which is what we proved in the recursive least squares, serial parallel recursive least squares, h, for example, can be just 1, and the condition is this needs to be SPR. Today we're going to work out a scenario where the adaptation gain is time varying following this is the general adaptation gain formula. I wrote it in an inverse structure to save some space, but it has an equivalent structure where you write things in a fk plus 1 equal to fk minus something. The conclusion is we needed just a little bit more in the LTI block. We need this minus sign and half of lambda being SPR, where lambda is the maximum of the lambda 2 over here. In a first glance, we see still some good news. For example, in recursive least squares, if it's with time varying adaptation, then we can see that the condition for hyperstability is that we need 1, h is 1 in that scenario. 1 minus half of lambda needs to be SPR. And for those who really dig into all the details, you will notice when we defined lambda 2 in this way, there are some conditions for lambda 2, which is what? Is actually this. So if lambda is the maximum of lambda 2k, then you can see that this is really true. This is always positive, and it's SPR. So that's the good news. Our recursive least square that we worked out actually is also stable, even if the gain is time varying. And you can also appreciate the fact that it's the little extra here is making it slightly more difficult to be SPR. You're adding something that's negative to this LTI system. All right? If it's positive gain, it's always SPR. If it's negative gain, it becomes not SPR. The general scenario, the fact that we have to live with, is that if Fk is time varying, then this block itself, which is passive in the past, is no longer passive. So this block is not passive. We have to do something else to make it passive. And the technique is actually what we have been using multiple times in this class. Is as follows. So we have the same theta equation. We're going to add a few things and subtract a few things to create a nonlinear passive block diagram. All right? The simple fact that we can appreciate is, suppose, let's say we have a system, first system, we know the fact that if the two systems are both passive, the feedback connection is passive. Now, the second piece of good news is that if this is not passive, we can actually create a passive system by negative feedback. So the power of feedback is appearing here. Feedback can not only stabilize a system, that's what we all know, right? Undergraduate control system will tell you that if this is unstable, then you can stabilize it with something with feedback, negative feedback. Now the good news here is that even if this is not passive, there are ways to add something else over here to make the entire thing passive. And this is how. We're going to add and subtract a few things along this line. So I'm going to make this negative, this is plus, this is negative, this is plus. I'm going to add and subtract this block in the lower bottom over here, and add and subtract another block in the top part over here. The lower part, I'm going to add and subtract lambda 2k over 2. In the top, I'm going to add and subtract lambda over 2. I'm not changing the overall system configuration in this way. And then the nonlinear block in the end is going to be this one. The top part is linear LTI. The bottom part is the nonlinear part. So let's see how this will make the bottom part to be passive. This is add and subtract. Actually, let's work on the top part first. So the top part, we know is still LTI. This is LTI. This constant is also LTI. So it is still LTI. It looks like this. Let's modify this block diagram a little bit and make it look easier to analyze. This is equivalent to HQ. You can see these two are in parallel with each other. This is a plus sign, but there's a negative sign over here. So this is actually equivalent to this. Okay, so let's say this signal is alpha, this is eta. Then you can see the two block diagrams are exactly equivalent. Okay, in here, eta is going to be equal to HQ inverse times negative alpha plus half of lambda alpha. Then you can verify it's the same in the bottom over here. Let's work on the nonlinear part. So for the nonlinear part, we again, now if you recognize this kind of analysis, we can work on it this way. The bottom part we have equivalence to first of all, is a negative feedback of lambda 2k. The last two blocks over there, I'm just arranging these where I draw these signals. So I can arrange this to be here and pull this to be closer to the bottom. Then I have this. And then I'm going to have another block I'm going to combine these two. I have already used this branch. I'm going to combine these two into one. The signs are different. So you can see one is negative, one is plus. I'm going to combine them in a way to have half of lambda minus lambda 2k with a negative sign here. The intuition or the way that we're going to approach this proof is this. Lambda is, so this block over here is positive because lambda is the maximum of lambda 2k. So this is positive. And then this connection, this block with the whole bottom part is in a feedback structure and is in a negative feedback structure. So we're going to use this concept over here to prove the passivity. Let's work on, actually, there are two feedback blocks. This is also a tiny feedback block. And this is positive. Okay? So we're going to actually show first, this is passive. And then we have a passive block, another passive block in feedback. So the whole thing is going to be passive. So the only tricky thing is perhaps looking at the only thing new is this term. Let's define some signal notations first. I'm going to denote this as SK. The signal that comes out of this is WK. And we know in the past, so the signal WK is the signal here. So the signal out of this theta tilde block is what we have used in the past. It's theta tilde k plus 1 transpose phi k. So if this is SK, let's take a look at this signal here a little bit more carefully. It's going to be what goes into the theta tilde equation is epsilon k plus 1, right? Let's be careful what goes into the nonlinear block from our previous analysis. So with that cleared up, let's think about what we need to show. We need to show the supply, which is the input to this block, which is SK. This multiplied with the output is lower bounded by some negative number. All right? So it's now different. In the past, we showed this multiplied with this is lower bounded. This time is different. So what we need to show, need to work on this product term k from 0 to k1, sk wk is lower bounded by some negative gamma square. This would translate to summation sk in here. Sk and epsilon k plus 1 has a relationship, which is sk minus this signal equals epsilon k plus 1. And this signal is minus lambda 2k over 2 times this signal, which is w. And it equals epsilon k plus 1. In other words, we know that sk equals, let's write it out here, sk equals sigma epsilon k plus 1 plus lambda 2k over 2. Wk equals here, so I'm going to put it in now to write the regressor vector in the front. This is Wk. All right, so this also equals to, we can make it a little bit more explicit. Put Wk inside. All right? This is the explicit form. This part, we know, we have worked on this before. This epsilon times the WK term, we worked on this before. This is slightly new, but if you put this inside, multiply this inside, you can see this is going to generate a product that looks like this. Half I'm changing the orders of terms a little bit. But the product is going to give us something in the end. Theta tilde k plus 1 times lambda 2k, this phi and phi transpose term. Phi and phi transpose and then theta tilde. Now, this is actually something not foreign to us either. It appears on the left of the screen, actually. Right? It is the way how we update the regressor, the adaptation gain. So this actually is a function of F inverse and then lambda 1k. We have seen F inverse appearing before in the recursive least square proof, stability proof. So, and then this is a quadratic term. This is theta tilde transpose, something in the middle, and then theta tilde. So more and more hope in making it lower bounded. I'm going to write this equation out, and then put this relationship inside this product term to get, this is going to be a little bit long, but all the terms have a purpose. It's going to be plus half of theta tilde transpose, and then lambda 2k phi transpose. I'm going to use this fact over here. It's going to be F inverse k plus 1 minus lambda 1k F inverse k theta transpose, theta tilde. Next, we're going to do this. Recall, we still have the fact, the adaptation process. All right, so this time I finished this part, I'm working on this part now. I'm going to substitute, I'm going to use this connection here to change the first part a little bit more friendly. Phi times epsilon is going to be equal to F inverse k theta tilde k plus 1 minus theta tilde k. You can see now it's the same concept. I'm trying to create quadratic terms or cross product between something that will come out of a quadratic product. Then the rest, I'm going to copy it down here into then minus half of lambda 1k okay, break it into two. Now we see we can combine this with part of the first product here, and we can get half of theta tilde transpose. Then inside it's going to be 1 minus lambda 1k F inverse k theta tilde. Right? Half negative lambda 1k is this part. Then I'm putting half of it out from the first multiplication. So I have one more that I need to write it out. All right, so this finishes up here and here. For the remaining, we have half of theta tilde transpose F inverse. And then I have 1 minus this cross product. This term is still not so friendly. Let's do the same thing again we did last time. We're going to add and subtract something here. And the thing we're going to add and subtract is half of theta k F inverse. Let's try this. Okay, so we're going to add and subtract this. This term, and then this term. This is a quadratic function about theta tilde k plus 1. This is a quadratic function about theta tilde k. And this is their cross product. Look at this. Can anyone tell me what kind of quadratic formula this will give me? It's going to be something minus theta tilde k, the whole thing transpose, and then this. Right? Let's take a look. I won't write it out because it's going to be too long. But you can see I'm going to have half of theta tilde transpose, theta k plus 1 transpose, times F inverse times theta tilde. So I have this. And then I'm going to have a cross product, theta tilde transpose k plus 1 times F inverse times theta. So I'm going to get this as well, and this negative sign. And finally, I'm going to have this, the positive part of this added and the subtracted term. I'm going to have theta transpose k, F inverse theta tilde k. So these two are red underlined terms are the same. And then the rest is we have wrote out this. We need to count this inside, and then I'm gonna write it together with this. So I'm gonna write half of k plus 1 F inverse k plus 1 theta tilde k plus 1. I'm going to combine these two together and note this negative sign. That finishes this, the negative part, and then this part. What's left? The only thing left is this part. And this part is half of one minus lambda 1k F inverse theta tilde. And that's all. So now you can see the good news. This is quadratic, so it's always non-negative. This term is always non-negative. This term is also non-negative because we talked about how lambda 2 should be satisfied. And then lambda 1k, if you pay attention to the definitions, is this way. We designed the forgetting factors to be The first one to be less than 1, the second one to be less than 2. So this part is also always non-negative. The last part is the same thing that we have done before. This is the summation over k of these terms, and then we have the cancellation happening exactly the same in the recursive d-square formula. This time, after the summation sign, is going to be larger than or equal to negative half of, actually I want to write 2 steps. It's going to be larger than or equal to half of theta tilde transpose k1 plus 1. The 2 boundaries, essentially. Minus half of 0, 0, the initial value. This larger than or equal to sign is because of these 2 terms to be larger than or equal to 0. And then this term, the final result that we're going to need is actually this term is also non-negative. So this is lower bounded by this negative gamma square. This is a gamma square. And then we have it. This is indeed lower bounded by something that's negative. Okay? Now we have proved that this block is passive. All right? And then use the final element to add in. So now we have dashed block passive. And then this whole thing, this is therefore a feedback connection of 2 passive blocks. So the nonlinear block is a negative feedback connection of 2 passive blocks. So therefore, the nonlinear block is passive. So this completes the whole picture now on the board. The result is that this is passive, and then the LTI block is HQ minus lambda over 2, and we need this to be SPR for the whole asymptotic hyperstability.